Welcome to our second video of complex analysis. In this lecture, we will discuss on complex variable function. Before starting complex variable function, at first we want to discuss on complex variable. What is a complex variable? In our previous lecture, we saw a complex number or any number that is consist of a real part x and an imaginary part y is known as complex number. If we use this complex number as variable in a function as variable, then we will get two parts. One is real part or one is real function, let it be u, and another one is imaginary part or imaginary function. Then fz is called complex variable function. I repeat, students, a complex number. If we use a complex number as variable, then it's called complex variable. If we use any complex number as variable in a function, then we will get there two functions, whereas one is real function and another one is imaginary function. Then fz is called complex variable function. So what is a complex variable function? The function whose variable is a complex number is called complex variable function. A function whose variable is a complex number is called complex variable function. Now a question: if z equal x plus iy, then show that fz equal z square is a complex variable function. Okay, solution. Given z equal x plus iy, we need to prove fz equal z square as a complex variable function. We know if a function is a complex variable function that it must have two parts, whereas one part is real part, that means a real function, and another one is the imaginary part, that means imaginary function. If we can divide z square into two parts, there where one part will be a real part and another one is a imaginary part, then it will be a complex variable function. So let's divide it. X plus iy to xy. Here it's x square minus y square plus I into 2xy. Therefore fz equal this. Look students, here fz equal this plus this. There's no I, that means it's a real part and it's a imaginary part. We can denote this as u xy and it as v x, y. This fz is consist of two parts, where this is real part, that means real function, and this imaginary function. That's why we can call fz as complex variable function. That's why fz is a complex variable function. Another important topic of complex analysis is analytic function. So what is analytic function? If a function is analytic, then it always satisfies two conditions. Any complex variable function is called analytic function if it satisfies the following two conditions. The first condition is the function must be single valued function, and second one, continuous and unique derivatives at each point of domain. There one question come to our exam. Check the function fz is analytic or not. This kind of questions sometimes come to our exam. Check the function fz is analytic or not. To solve such kind of question, we actually don't use the above two conditions. For this, we have a unique way, and its name is CSIR equation. So let's see what is the CSIR equation and how we'll solve this kind of problems using CSIR equation. CSIR equation is very important part of complex analysis. CSIR equation means Cauchy-Riemann equation. Cauchy-Riemann equation. Given fz equal u plus ib. Let it be a complex variable function where u is a real function and v is a imaginary function, and two conditions: partial derivative of real part with respect to x equal to partial derivative of imaginary part v with respect to y. Partial derivative of real part u with respect to y equal to minus partial derivative of imaginary part with respect to x. These two equations are known as CSIR equation. If any function satisfies these two equations, then it is called analytic function. If a function satisfies these two equations. Then it is called analytic function. So here these two equations are CSIR equations. It's the statement of CSIR equation. In this video we want to prove these two equations. We will prove these CSIR equations in our next video, not in this video. Here we need the statement only. So here if a function satisfies these two equations, then it is called analytic function. But all the functions who satisfies CSIR equation may not be analytic at any particular point, because at that point the two conditions of previous, that means the two conditions of to be analytic that we discussed previous may not be satisfied. That's why let's see how will we use these CSIR equations to test a function is analytic or not. Take a question, check fz equal 1 by z is analytic or not. We will solve this by using CSIR equation. Okay, see these CSIR equations. These CSIR equations are for a complex variable function like this. So we have to divide fz into two parts like u plus iv, given fz equal 1 by z, that means x plus iy equal here take the conjugate of x plus iy in both the numerator and denominator. The conjugate of x plus iy is x minus iy, and here x minus iy. So it will be x square minus iy whole square. It will be x minus iy equal, it will be x square plus y square. It will be x minus iy. If we divide this into two parts, it will be x by x square plus y square minus I into y by x square plus y square. Let it be u and it be v. Then this will be u plus I v. So it will be u and its v. That's why fz is now divided into two parts, where u is a real function and v is a imaginary function. Now fz is divided into two parts, u and b, where u equal this real part and b equal this imaginary part. So now we have, if we use CR equations here, we need to partial differentiate u with respect to x, b with respect to y, u with respect to y, v with respect to x. So let's do it. At first, if we partial differentiate u with respect to x, then it will be del u by del x is equal to x square plus y square 1 and this partial differentiate, that's why it's 2x and it's x square plus y square whole square. So it will be minus 2x square, that's why it will be y square minus x square divided by x square plus y square whole square. Now if we partially differentiate u with respect to y, del u del y, then it will be with respect to y, that's why x is constant now, will be x square plus y square whole square be minus 1 to 2y. So it will be minus 2xy x square plus y square whole square. Now we will partially differentiate b with respect to both x and y. So it will be del b del x is equal to with respect to x, that's why minus y is constant, it will be minus 1 is equal to 2xy x square plus y square whole square. Now we will partially differentiate v with respect to y. Square whole square square in y, that's why it's minus 1 minus y into this means 2y. So if we simplify this, it will be plus 2y square. That means it will be y square minus x square x square plus y square whole square. Okay students, since del u del x equal del v del y, that means del u del x equal del v del y, and del u del y equal minus del v del x, this and this. So we can tell fz satisfy CSIR equation. Satisfy CSIR equations. As it is satisfying CSIR equation, that's why we can tell it as analytic function. So fz is analytic. So we have seen that if a function need to be analytic, then it is always satisfies two conditions. But in exam we don't use those two conditions to test either it's analytic or not. So we use CSIR equation to test whether a function is analytic or not. It's all about today's lecture. Subscribe our channel to get our future videos. Thank you for watching.